Written homework 5, explanation of problem 1a. So the problem states a lamp has two bulbs. We have a lamp here, we have two bulbs. There we go. And each bulb has an average life of 1,000 hours. Okay, and the problem also states that we can assume the probability of failure of these bulbs can be modeled by the exponential density function with mean mu equal to the 1,000 hours. And it asks to find the probability that both bulbs fail within this 1,000 hours. So this lamp has two separate bulbs, and for the purpose of this problem, we are assuming that they are not in any way connected. So if one goes out, it is completely independent of the other one going out. So the probability of one bulb going out can be modeled by the equation E to the negative x over mu, all of this divided by mu, which we already said that this mu given to us in the problem is 1,000 hours. So this problem applies, or this expression applies to each bulb as long as we are talking about positive time. So we can say that the probability of bulb X blowing out, or the probability of one bulb blowing out, is this for X greater than 0 and is 0 for X less than 0 as a piecewise function. And where was I? So now to find the probability that both bulbs blow within any given time period, we can write this double integral. So the second bulb, we'll call this probability 1, and probability 2 is basically the same thing, but we're going to write it with a y, just to show that they are independent of each other. Although in this case, x and y are both time. These are or equal to 0. So to find the probability, we do a double integral of e to the negative x over mu divided by mu times e to the negative y over mu divided by mu. And since the two bulbs are assumed to be identical, they both have this mu of 1,000, and then we have dx dy. Now here the limits of our integral are going to be the time that it takes, or the time that we want to find the probability for them blowing over. So for both bulbs it is 0 to 1,000 hours. If we wanted to know different times for the different bulbs, then we would need to put different numbers in these bounds. So we do this multiplication here because assuming these are independent variables, which they are, the probability of both x and y is equal to the probability of x times the probability of y. I'm running out of room there, but that's okay. So that's why we multiply these two density functions. Probability x and y. And this integral can be simplified by saying from 0 to 1,000 of e to the negative x over mu divided by mu dx times the integral from 0 to 1,000 of e to the negative y over mu divided by mu dy. Okay. So we are running out of space. All right. So to solve this, we're going to move over here. There we go. Probability of x and y is equal to 1 over 1,000 times the integral from 0 to 1,000 e to the negative x over 1,000 dx times 0 to 1,000 e to the negative y over 1,000 dy. I just pulled out this 1,000 and this becomes 1 over 1,000, or no, sorry. This becomes negative e to the negative x over 1,000 evaluated from 0 to 1,000 times negative e to the negative y over 1,000 evaluated from 0 to 1,000. Here, there we go. This 1,000 goes away because of the u substitution that we do here, where u is equal to negative x over 1,000. And I guess it would be easier to see if we left each of them in here. So du is equal to negative 1 over 1,000 dx. So that's where that 1,000 goes to. and we can either change our bounds or just plug the u back in. So this gives negative, well, the negatives cancel here, so this negative cancels with this one. So this gives e to the 0 minus, no, e to the 1 minus e to the 0 times, this is e to the negative 1, sorry, e to the negative 1 minus e to the 0. Sorry, quick break there. All right, so this is, we do this, we see we have 1 over e minus 1 squared. And that's as far as we're going to go calculating it up there on the board. Now, because this is a probability, this doesn't tell us much, so we really want to know what that is in decimal form. So we're going to take the calculator, 1 over e minus 1, and square it. And this comes out to approximately 39.96%. So what this means in the context of this problem is that there is a 39.96% probability that both bulbs will blow out before the 1,000 hours, or before the 1,000 hour average for each bulb.